All right, so we're looking at page 51, specifically implicit differentiation, and this very vague question of find the derivative of f of x comma y equals 0. Kind of a strange question because it's in general terms, but it doesn't really seem like it's giving us any kind of direction as to how we would go about doing that. Right? So the first thing that we'd have to assume is that, based on the notation, it's logical that f is a function of x and y. We'd also have to assume that x and y themselves could also be functions. All right? So x is a function, and so is y. All right. Now that function is belonging to the set of all real numbers, and it could have some sort of relationship, but we have to have the freedom to allow x to be a free variable, in the sense that x would be just simply a function of x, and y would be a function of y. So basically, x is x and y is y, because we can't define it any other way necessarily, because we didn't introduce any other parameters. All right, so when I go to take the derivative of this, it depends on what I'm taking it with respect to. We have a couple of different possibilities. All right, so the first thing I can do is take the derivative of that with respect to x. All right, or I could do it with respect to y. All right, so I'm going to go back to my chain rule tree diagram concept and say, okay, I'm starting off with f, and I'm going to break that up by partials and say I'm going to have the derivative with respect to x, partial with respect to x, partial with respect to y. But then from there, I'm going to say that I can take the derivative of x with respect to x, or I could take the derivative of x with respect to y. It wouldn't be a partial derivative anymore because it would be a function of a single variable. All right, so in this case, since it's not multivariable, I would just simply write it as, well, I'll go with the, this is x part first. So it could be dx dx or dx dy. I could take the derivative of the x equation, if you will, x function with respect to the variable x, or I could take the derivative of the x variable with respect to y. Okay? Same or similar idea when it comes to the partial with respect to y. I could take the derivative of the y function with respect to x, or I could take the derivative with respect to y. All right. So when I go through the process of finding a derivative, one thing I could do, if I'm actually looking for the derivative, so d dx of the function in terms of x and y, oops, close the bracket, is I could write that following the pathway that gets me to an x, or pathways. That would be these two. So going down this road, then going down this road. So I could say it's partial f with respect to x times dx dx, which just amounts to a 1, plus partial f with respect to y times dy dx. Now they said find the derivative where the function is equal to 0. Right? So the assumption here is if I want the derivative of this whole thing, this whole equation, I would assume that I'd be taking the derivative of the right-hand side also. But that's easy enough. I'm going to resize. The derivative of 0 is equal to 0, no matter what the variable is. So d dx of 0 would be equal to 0. All right, so now I can set these two expressions equal to one another, and that would give me, so therefore, wrong kind of d, delta f, partial f with respect to x plus partial f with respect to y times dy dx would be equal to 0. Now, for the sake of not losing my mind with the notation here, I'm going to rewrite this as capital F sub x plus capital F sub y dy dx is equal to 0. And then that would give us, when we solve for dy dx would be equal to negative partial derivative with respect to x over the partial derivative with respect to y. All right. So it kind of begs the question, well, what if we did all that, but with respect to y? You can probably see how a different pathway would come into play. We'd be going down this road. All right, so if I were to do that, I'd be looking at derivative with respect to y of f of x comma y. That would be the partial with respect to x. So I'm going to write f sub x multiplied by dx dy plus the partial with respect to y multiplied by dy dy, which is going to amount to a 1. Same general idea, we're setting it equal to 0, d dy of 0 is equal to 0. So I'd have the relation f sub x dx dy plus f sub y equals 0, which gives us dx dy, which is equal to negative f sub y over f sub y. All right. Now, it kind of begs the question as to why we would have to do this if ultimately we were looking for dx dy. Well, isn't that just the reciprocal of this? Take the reciprocal and you get that relation. All right, so, but it's a nice little way to prove it, and it also ties together nicely with the chain rule. Okay. More importantly, it gives us a way of finding a derivative of an implicitly defined multivariable function without having to go through the process of solving it explicitly first. All right, so you see in the case of number 1, xy squared minus e to the xy cosine x equals 0. All right, so what it's asking us to do here, we have our function defined. The left-hand side is the f of x sub y, x comma y, I should say. If I want dy dx, I just need the partial with respect to x negated divided by the partial with respect to y. All right, so f sub x. Now, sometimes it's easier said than done, but it's still doable. All right, so the variable is x, so I'm going to leave the y squared as is, differentiate around it, minus the derivative of e to the xy. So this is product rule, because both parts involve an x. So the first function times the derivative of the second, plus the derivative of e to the xy, I was about to say this earlier, but it would have been premature, is going to be e to the xy multiplied by y times the derivative, so that is the the derivative of the first. I kind of did it out of order. I apologize. But it's the first times the derivative of the second plus the second cosine of x. I get a little eager beaver here. Second times the derivative of the first. All right. Then f sub y is going to be equal to, you're going to differentiate again, just this time with respect to y. It's actually going to be a little easier because x is treated as constant. Derivative of y squared is 2y, so 2xy. Then the only part I have to worry about differentiating would be this piece, the e to the xy, because cosine of x is coming along for the ride because it's treated as constant. So e to the xy, the derivative of xy with respect to y, so y goes to 1, so it's just an x. So if I want, or if I wanted, dy dx from all this, all I'd have to do is negate the numerator or denominator, whatever is more convenient, right? And then make a ratio out of it. So that's what I'm going to do. I'm going to negate. I'm going to take first. I'm going to look at it strategically and see which part makes more sense to negate. In this case, I don't think it really makes much of a difference. I got to slap a couple of negatives in here. So I'll put one in front of the y squared, and I'll make this minus into a plus. So that takes care of negation. They made a fraction bar, so that made it a ratio. And so that would be your derivative. Like I said, it ain't pretty. Frankly, I don't know if I actually said that, but I'm saying it now. So there we are. Now, for number 2, you see it's a function of 3 variables. The first step in the process would be to get everything over to the same side so we can work on it implicitly. Minus xyz equals 0. Now you see here we're asked to do it for 2 different partial derivatives. All right, now since it's a function of 3 variables, we're looking at this being f of xyz. So instead of finding the derivative of y with respect to x or x with respect to y, it's z with respect to one or both of the other 2 variables. All right. So we'd go up to this this definition that brings it up into the appropriate dimension. But you can see it's still relating partials. This time it's the ratio of partial x with respect to z and partial y with respect to z. All right. So I need all the partials anyway, so I might as well just kind of get to work on it. Some problems easier than others. This one's not terrible because the e to the z doesn't have an x or y in it, so that's treated as constant. All right, so when I take the derivative, I lowercase this f here, apologies. It really doesn't matter if you decide when you're calling it a function that you're designating it as, like if you call it lowercase or uppercase. It's just since we're already referring to it as uppercase, we got to be consistent. All right, so yeah, the e to the z goes to 0. The variable in question is x, which is going to go to 1. So this is just negative yz. Differentiating with respect to y, again, e to the z goes to 0. Y goes to 1, so negative xz. Differentiating with respect to z, e to the z goes to e to the z. In the first part, and the second part, z goes to 1, so e to the z minus xy. All right, so if I want partial z with respect to x, I'm taking the negation of partial x, which would just be positive yz, and dividing it by partial with respect to z, so e to the z minus xy. And then I'm taking partial z with respect to y's equation, which is the negation of partial y, which is xz, divided by the same denominator. And those would be your derivatives using an implicitly defined function. So the alternative to that, you look at maybe the first example and you start kind of brainstorming about different ways in which you could solve for y in terms of x. But when it comes to the second one, you know, it's along the same lines. It's the e to the z here that messes everything up. Just like in number one, the e to the xy sort of messed everything up. So even if you could solve for y in terms of x for the first equation, that doesn't necessarily mean that you would be able to solve for z in terms of x and y for the second equation. In which case, defining it as a multivariable function, just including the dependent variable as if it were an independent variable in a new function. So basically we're taking a really something that could be rendered in 3 dimensions, but we're shooting it up to the 4th dimension so that we could use 4th dimensional techniques to differentiate and then bring it retroactively back down to the 3rd dimension. All right, so that's sort of the rationale here. And in a lot of ways, we're taking a good amount of this on faith, but that's why we start off with the stuff that we can verify, you know, because for this one, you could use, for number one, you could use good old-fashioned implicit differentiation, you know, like from Calc 1. And then in that process, solve for dy dx. You will get something that may not exactly look like this, but it'll be equivalent to it. Right? And so that's the idea. That you can verify it in the dimensions that we're comfortable with, and use it to, with good amount of logic involved, project out into the higher dimensions. All right, so then number 3, same idea. It's a function, in this case, of 3 variables on the left-hand side. If you could extract the z so that you could solve for z in terms of all the other variables, then you'd have a different technique that would be at your disposal. Not the case here, though. Because if it's doable, it's not easily done. So f sub x, so derivative with respect to x. So all the x's are the variables. So we're looking at y squared plus the z cubed goes away, cosine of xyz times the derivative on the inside with respect to x would be yz. Just thinking here, it probably would have made a lot more sense if I actually read the problem before I started working, because it says partial with respect to y. So it's only this case that's relevant. So I actually didn't need to do what I just did. That being said, it's good practice, I guess. Just irrelevant. So f sub y, 2xy, the z cubed, irrelevant, plus cosine xyz times the derivative with respect to y would be xz. And then the fun one. There's usually one that's fun. All right. In this case, it's actually equivalent difficulty, but it's always good to kind of have that in mind. You look at it and say, all right, well, one of them's going to be the more challenging one. Which one is it? You know? So xy squared is irrelevant because it doesn't have a z in it. 3z squared. Sine goes to cosine, still xyz. The derivative of xyz with respect to z would be xy. All right, and so if I want partial z, or quality z, with respect to y, I just need to negate my f. All right, so negative. Make a nice fraction and put it over my, I think I just said negate my f, they're all f. Negate my f sub y. and then divide it by my f sub z. That was one of those moments where it's like, did I just say what I think I just said? Classic Bob. My name's not Bob, though. Still, nobody's gotten that TV show reference. If somebody does, there's bonus credit in it for you. All right, so yeah, there we are. That is the concept of implicit differentiation.